Welcome back, KSDS scientists. Today we're going to continue with our essential question, what is the relationship between force and motion? And we have finally made it to the third and final of Newton's laws of motions. So today we're going to talk about Newton's third law. So Newton's third law states that if one object exerts a force on another object, the second object exerts a force of equal magnitude, meaning strength, but in the opposite direction on the first object. So for example, when this hammer hits the nail, okay, this arrow here could represent the force of the hammer on the nail. Let's say it's 100 newtons in the positive direction. So if the hammer exerts a force of 100 newtons on the nail, then according to Newton's third law, the nail also exerts a force of 100 newtons on the hammer. However, it's in the opposite direction. So equal in magnitude, but opposite in direction. So we call these pairs of forces action-reaction pairs. So for example, this fish, as it swims through the water, the fish's fin exerts a force on the water. So we have the force of the fin on the water pushing it back. So then the water pushes on the fish in the opposite direction. So the force of the water on the fin. So this is an example of an action-reaction pair. Here we have Messi about to kick this soccer ball. So the force of his foot on the ball could be the action, and then the force of the ball on his foot would be the reaction. So again, another example of an action-reaction pair. Here's one you may not have thought of before. So we know that Earth pulls down on us with a force that's equal to our weight, right? Determined by our mass and the gravitational pull of the Earth. Well, you actually pull up on the Earth with a force that is equal to the force that the Earth pulls down on you with, but opposite in direction. So while the Earth is pulling you down right now, you are actually exerting a force to pull the Earth up. So the force of the Earth on you and the force of you on the Earth. Now you might be going, wait a minute. The Earth isn't like, jumping up. If I'm at the top of a building and I jump off, I get pulled down to the Earth, but the Earth doesn't get pulled up towards me. So what's going on here? So there's a few things we need to keep in mind, some common misconceptions that we don't want to fall into. So action-reaction forces do not result in equilibrium. So you might think, if all of these forces are equal in magnitude, then how does anything move, right? But equilibrium is when you have two forces in the opposite directions that are equal in magnitude acting on the same object. Action-reaction forces are acting on different objects. So remember, the hammer was exerting a force on the nail, and the nail was exerting an equal force on the hammer. So you have two forces going in opposite directions, but they are on different objects. They're not on the same object. So each of those objects independently is not in equilibrium. Also, the motion that results from these forces is going to depend on an object's mass or inertia. You weigh a lot less than the Earth weighs. So when the Earth acts on you with a certain amount of force, it could cause a really big change in motion, right? It could cause you to fall from the top of a building to the bottom. But when you exert an equal force on the Earth, because the Earth weighs so much, remember F equals ma, right? So we can divide both sides by mass. So acceleration is determined by force over mass. So if mass is really, really big, if this number on the bottom is really, really big, then acceleration is not going to be big at all. So we're taking the same amount of force, but we're dividing it over a much, much, much greater mass. Of course, we can also relate this back to Newton's first law, the law of inertia. So you have a lot less inertia than the Earth, so it's a lot easier to change your motion than it is to change the motion of the Earth. It would take a lot more force in order to do that. All right, that's it. Thanks for watching.